Welcome to today's lecture. Today we are going to continue from where we had left in the previous lecture. So today we are going to study about the machine foundations which are resting on piles. Now, as far as an individual pile is concerned, an individual pile does have adequate capacity against vertical vibrations and also against horizontal vibrations. So if we are drawing the coordinate system as per our convention for the machine foundations with the x and y axis lying in the horizontal plane, then a single pile does offer the stiffness in the vertical directions Kz and also the stiffness in the horizontal direction, which could be Kx or Ky. However, a single pile is not sufficient from structural engineering point of view to offer bending stiffness K theta x or K theta y and also the torsional or the yawning stiffness K theta z. For the case of the bending stiffness or the torsional stiffness, we need minimum 2 piles. For example, here we are showing the elevation with 2 piles connected by a pile cap at the top, and here a bending moment My is applied. So basically this is resisted in terms of the push and pull effects in the 2 piles. So essentially it's the vertical stiffness Kz which is leading to the bending stiffness K theta y or K theta x. Similarly, for torsion or the yawning resistance, so here we are showing a group of 4 piles and this is planned, so we are seeing the axis x and y, and if any torsional moment is applied, then that torsional moment is resisted on account of the horizontal stiffness Kx or Ky. So essentially it's the horizontal stiffness of the individual pile that gives rise to K theta z or the stiffness for torsion or yawning stiffness. So that's why in general a group of piles is necessary in the case of machine foundations to provide adequate stiffness against various kinds of motions. So as far as a pile group is concerned, we can summarize the source of various kinds of stiffness. So in the vertical direction, it is basically Kz of the individual pile that gives rise to the vertical stiffness of the group. Now the individual pile may be an end bearing pile or it could be a friction pile. So accordingly, the source for Kz could be the end bearing reaction or it could be friction. Now, as far as the horizontal stiffness of the pile group is concerned, which we are denoting by Kx or Ky, so the horizontal stiffness basically results from again the horizontal stiffness of the individual piles on account of the modulus of subgrade reaction. As far as the bending stiffness is concerned, because the individual piles do not have any bending stiffness, so the bending stiffness of the pile group results from the vertical stiffness kz of the individual pile. So whether we are talking about k theta x or k theta y, the contribution is on account of the vertical stiffness kz. So basically the push-pull effect that leads to the bending stiffness. Now as far as the torsional resistance of the pile group is concerned, we have already seen that the application of a torsion moment or yawning moment basically tends to push the individual piles against the soil in the horizontal direction. So as such, it is dependent on the horizontal stiffness kx or ky. So we have concluded that in order to obtain the stiffness of a pile group, we need to obtain two important stiffnesses of individual pile, that is the vertical stiffness and the horizontal stiffness. Let us begin with vertical stiffness of an individual pile. Basically, the vertical stiffness of an individual pile will depend on whether the pile is end bearing type pile or a friction type pile. So we will evaluate both these cases individually. Let us begin with an end bearing pile. A pile is an end bearing pile when the soil surrounding the pile is essentially a loose or weak soil, and at the bottom of the pile there is a very stiff soil or a hard rock. Let L be the embedded length of the pile, and above the pile the superstructure is contributing a weight Ws, which is in newtons. In order to idealize the pile, we can consider that the lumped mass at the top of the pile contributed from the superstructure is Ws by G. So here Ws is in newtons, so that's why we are dividing it by G. However, if it's given in tons or in kgf, then we don't need this division. So we can obtain the mass lumped at the top of the pile, and we denote it by symbol ms. Then for the pile which has its own self weight, we consider 1/3 of the mass of the pile to be lumped at the top. So essentially we can idealize the pile like a spring with a mass at the top equal to ms, that is from the superstructure, and 1/3 of the mass of the pile itself. So here the end bearing pile is idealized as a rigid bar undergoing axial vibrations. So the standard solution is available in any book of structural dynamics. The natural frequency is given by this relationship. So here omega n is equal to beta by L under root E by rho. E is the Young's modulus of elasticity and rho is the density of the material of the pile. So here Omega n is in terms of radians per second because it's the angular frequency. The constant beta is given by this relation. Beta tan beta is equal to alpha, which is the ratio of the mass of the pile to the mass lumped at the top. So this solution is available in table 3.5 of the textbook, which is being reproduced here. Once the angular frequency of vibration of the end bearing pile is obtained, it's quite straightforward to obtain the vertical stiffness, which is essentially the mass times the square of the angular frequency. So the mass to be considered here is the mass lumped at the top of the pile from the superstructure plus the portion contributed by the pile. So we can write an expression 1 plus alpha by 3 times ms. Next, let us consider a friction type of pile for determining the vertical stiffness Kz. Essentially, a friction pile is a pile which has a loose soil at its bottom. However, the soil surrounding the pile itself offers a good source of friction as shown here. However, there is an important consideration of the pile to pile distance. So for the friction all around a particular pile to be effective in a group, it's necessary that the piles should have sufficient spacing. It's preferred that the spacing between the piles should be greater than 6 times the diameter of the pile for the individual friction effect to be effective. Otherwise, if the piles are very closely spaced, then the group effect will dominate. That means that instead of the individual piles acting with their friction, it will be the group of the piles as a whole that will tend to behave like a single unit, and as such the surrounding area mobilized would be much less as compared to the individual areas. As we'll see that the capacity of the pile in friction depends on the effective area in contact with the soil effective in mobilizing friction. Therefore, in case the spacing is less than 6 times the diameter of the pile, then a correction factor is to be introduced to take care of the group effect. However, in no case the spacing between the piles should be less than 3 times the diameter of the pile. The vertical stiffness of a friction pile is given by the product of the coefficient Cp multiplied by the surface area of the pile in contact with the soil. So basically it's this area pi dl which is directly mobilizing the friction. For the individual pile effect to be valid, the spacing between the piles should be greater than 6 times the diameter of the pile. However, in case the spacing ratio lies between 3 to 6, then a correction factor alpha is to be introduced. So here we are reproducing a table from the textbook where the value of Cp is given by the former Soviet code, and we are also reproducing the values of alpha when the spacing ratio is in between 3 and 6. Let us now study the expression for the horizontal stiffness of a pile. Under a horizontal load, pile essentially deforms in the fashion shown here. So as we go deep inside the soil, we encounter a point of fixity such that the pile undergoes a deformation just like a guided cantilever, that is a cantilever with fixed support at one end and a guided roller at the other. So this particular length is called as the length of fixity of the pile. It typically ranges from 1/4 to 1/2 of the total length of the pile. So from elementary structural analysis, we can write an expression for the horizontal stiffness of the pile in x or y direction as 12 EI divided by cube of the length of the pile to the point of fixity. So now this I would be IY or IX depending on which K value we are trying to compute. In case of Kx it will be Iy, and in the case of Ky it will be Ix. However, usually the piles are circular, so both the moment of inertias are in general equal. It should be noted here that this value of the horizontal stiffness of a pile is not dependent on the nature of the pile, whether it is friction pile or end bearing pile. This expression is same for both categories of the pile. After having learned the expression for the vertical and the horizontal stiffness of a single pile, we can very easily obtain the values for groups of piles, because usually we have groups of piles supporting a machine foundation. So here the analogy is just like for the case of the elastic pads, and essentially we follow the computation which is usually used in the case of steel structures for groups of rivets. So if we are showing here a group of piles with the horizontal axis x and y, and let's say there are n piles, all piles are identical and the group is symmetrical, then the expression for the vertical stiffness of the group will be simply n times the vertical stiffness of an individual pile. In the same manner, For the stiffness in the horizontal direction, say kx of the group will be n times kx of the individual pile, and same analogy holds for the stiffness in the other direction, ky. So usually the pile being circular in shape, the stiffness are same. Now when it comes to the group stiffness in terms of bending about the y-axis, then just like in the case of the elastic pads, it's given by kz multiplied by summation of xi square, which we have derived for the case of the elastic pads. Similarly, the stiffness of the group in bending about x-axis is given by the product of kz of the individual pile multiplied by sum of the squares of the coordinates of the piles along y-axis. Now finally, for the group stiffness about z-axis, that is the torsion, which is also denoted by k phi or k xi. So that depends on the horizontal stiffness. So what we have done is we have multiplied with the sum of squares of the radial distances of the centers of the piles from the overall CG of the system in plan, and this can also be written in terms of xi square plus yi square covering all the piles. So thank you very much. If you have any questions, you can discuss them during our interaction in the MST.